Somewhere in a NASA server, a photograph exists that someone decided you should not see yet. In October 2025, the most powerful camera ever sent to another planet captured an interstellar visitor from the side, an angle impossible from Earth. That image should have changed everything we understand about objects from beyond our sun. Instead, it vanished into bureaucratic review, held behind closed doors while conspiracy theories flourished, and the comet sped away at 30 kilometers per second. The official reason is a government shutdown. The HiRise website calls these images NASA-wide news, and we are left to wonder what they might actually show. Stay with me until the end, because what emerges when those files finally unlock might rewrite our place in the cosmos. Something extraordinary happened in the darkness between worlds, and someone decided you shouldn't know about it yet. On October 2nd, 2025, NASA's Mars Reconnaissance Orbiter aimed its HiRise camera at a visitor from another star system. The target was 3I Atlas, an interstellar comet screaming through our solar neighborhood at speeds that defy casual comprehension. HiRise captured images that should have revolutionized our understanding of objects from beyond our sun's domain. Those images exist right now, sitting in digital storage somewhere within NASA's labyrinthine infrastructure. You cannot see them. Nobody can. The delay is official, documented, and according to the HiRise website itself, these photographs are considered NASA-wide news. Translation: what they captured is significant enough that releasing it requires coordination at the highest levels of the agency. The stated reason for the holdup is a United States government shutdown. Bureaucracy has supposedly frozen the pipeline between raw data and public release. Reddit threads overflow with commentary from frustrated astronomers and space enthusiasts who smell something off about the timeline. Some voices in the scientific community are less diplomatic. Avi Loeb, the Harvard astrophysicist who suggested Oumuamua might be an alien artifact, has publicly questioned why NASA would withhold data about an interstellar visitor. His implication hangs in the digital air like smoke from a distant fire. Are they reviewing the images before release because of what those images show? Here is what makes the HiRise observations fundamentally different from everything that came before. Every telescope that has examined 3I Atlas from Earth or Earth orbit has viewed it essentially edge-on, seeing the comet as a bright smudge with a tail extending away from the sun. Hubble watched it. The James Webb Space Telescope analyzed its chemical signature. Ground-based observatories tracked its motion across the sky. All of them suffered from the same geometric limitation. They were looking at the comet along its direction of travel, compressed by perspective into a two-dimensional puzzle. Mars. Reconnaissance orbiter saw 3I Atlas from the side. The geometry of the flyby positioned MRO approximately 29 million kilometers from the comet, viewing it at an angle no Earth-based instrument could match. HiRise can resolve details down to roughly 30 centimeters on the Martian surface from orbit. At 29 million kilometers, that resolution is degraded, but still represents the highest resolution imaging of an interstellar object ever attempted. If there are structures on 3I Atlas, jets erupting from specific locations, asymmetries that suggest internal activity or something stranger, HiRise would see them. The stakes involve something called the anti-tail, a feature that has divided observers since the comet's discovery. Normal comet tails point away from the sun, pushed by solar radiation and the solar wind. 3I Atlas appears to have developed a tail pointing toward the sun. Anti-tails are not impossible in conventional comet physics. They can form when dust grains get left behind in a comet's orbital plane, creating an illusion of a sunward tail when viewed from certain angles. But some observers claim 3I Atlas's anti-tail is too pronounced, too structured, too persistent to be a mere projection effect. If the HiRise images show that anti-tail from a side angle, the question resolves immediately. Either it is real, a physical jet of material somehow moving against the solar wind, or it vanishes, revealed as the geometric trick skeptics always claimed. Online speculation has evolved beyond patient scientific discourse into something more fevered. Communities on Reddit dissect every available image, every statement from astronomers, every data release delay. Some threads discuss structured jets with geometric regularity. Others float the possibility that 3i Atlas is not entirely natural, that its acceleration profile and compositional oddities add up to something we have never encountered before. The word alien appears with disturbing frequency, sometimes as humor, sometimes as genuine hypothesis. Loeb's willingness to entertain non-natural explanations has given permission to others who might have stayed silent. The scientific fringe and the scientific mainstream are having the same conversation, just in different vocabularies. Consider the timeline. 3i Atlas was discovered on June 10, 2024, by the Asteroid Terrestrial Impact Last Alert System in Hawaii. It announced itself as an interstellar visitor through its hyperbolic trajectory, an orbit that will carry it permanently away from our Sun. It reached perihelion, its closest approach to the Sun, on October 1, 2025. The Mars flyby occurred essentially at perihelion when the comet was most active, most photogenic, most likely to reveal its secrets. HiRISE captured its moments of maximum scientific value. And then, silence. What if the anti-tale is real? What if there are collimated jets erupting from discrete locations on the nucleus, implying internal heat sources or volatile reservoirs arranged in patterns that challenge formation models? What if the surface shows features that require explanation beyond, "this is how comets look"? What if someone at NASA reviewed the preliminary images and decided the public release needed additional context, additional peer review, additional time to prepare the world for what comes next? We have sent space telescopes into the cosmos. We have built orbiters around Mars that can read license plates from orbit. We have developed the technology to intercept visitors from other star systems with high-resolution cameras at precisely the right moment. But we cannot control what those cameras see. 3i Atlas is leaving. Its velocity carries it outward past Mars, past Jupiter, eventually beyond the heliopause into the space between stars. This is our window. This is the moment when distance and geometry align to give us the clearest possible view of an object that formed around another sun, that traveled for millions or billions of years through the cosmic void, that passed through our solar system for reasons we do not understand. The HiRISE images are the best we will get, and they are being held behind closed doors while bureaucrats argue about government funding and data release protocols. You should be angry about the delay. You should also be terrified about what it might mean. Mars Reconnaissance Orbiter is not a glamorous mission anymore. It launched in August of 2005, arriving at Mars in March of 2006. By 2025, it is a geriatric spacecraft, nearly 20 years into a mission designed for a fraction of that lifespan. Its instruments creak with age. Its solar panels degrade. Its computer runs on architecture from the early 2000s. And yet, when the moment arrived to photograph an interstellar visitor, MRO was perfectly positioned, carrying the most powerful camera ever sent to another planet. The geometry of the October 2nd and 3rd encounter placed MRO approximately 29 million kilometers from 3i Atlas. For context, that is about 1/5 the distance from Earth to the Sun, closer than Mercury orbits on average. China's Tianwen-1 orbiter also captured images from a similar distance, releasing them publicly within days. Their images show a fuzzy blob with a visible coma, the cloud of gas and dust surrounding the comet's nucleus. Resolution is poor. Details are absent. But China released what they had, while NASA holds its cards. Previous observations from Hubble and James Webb suffered from perspective. Imagine trying to understand the shape of a car by staring at it directly from the front. You see headlights, a windshield, maybe the outline of the hood. You do not see the profile, the length, the way doors are arranged along the side. 3i Atlas has been observed from Earth as if we are standing on a highway watching it drive directly toward us. MRO was standing beside the highway, watching it pass in profile. Every structural detail, every asymmetry, every unexpected feature would be visible in a way Earth-based telescopes could never achieve. James Webb Space Telescope examined 3i Atlas in September of 2025 using its NIR spec instrument. The results were published on the Arcshiv preprint server, available to anyone with an internet connection and the patience to read scientific papers. Webb detected carbon dioxide, water, carbon monoxide, dust, and trace amounts of carbonyl sulfide. The composition is odd. Most comets in our solar system are water-dominated, with carbon dioxide as a secondary component. 3I Atlas is carbon dioxide dominated, with one of the highest carbon dioxide to water ratios ever measured in a comet. Either it formed in an unusually cold region of its parent star system, where carbon dioxide freezes preferentially, or something happened during its interstellar journey to alter its surface composition. The Swift Space Telescope detected hydroxyl, a fragment molecule that indicates water, at distances where water should not be sublimating efficiently. Comets closer to the Sun heat up. Their ices turn directly from solid to gas, and that outgassing creates the coma and tail. 3I Atlas was detected releasing water vapor far from the Sun, implying either an extended source of icy grains in the coma, or unusual surface properties that allow sublimation at lower temperatures. Models suggest a large fraction of the comet's surface is active, more than typical solar system comets. Active regions mean jets, localized areas where gas escapes preferentially, and jets mean structure. Ground-based telescopes captured 3I Atlas on October 31st, 2025, as it emerged from behind the Sun after perihelion. Qicheng Zhang, an astronomer who has built a reputation for capturing spectacular comet images, photographed it using the Lowell Discovery Telescope. His images reveal multiple jets, at least 7 distinct features extending from the central condensation. Some of those jets appear to point in directions that violate intuition. Anti-solar jets, structures extending toward the Sun rather than away, show up clearly. Multiple observers report the same features independently, reducing the chance of artifact or error. 3I Atlas is brightening. Before perihelion, predictions suggested the comet would reach a certain magnitude, a measure of brightness visible from Earth. After perihelion, it is brighter than expected. Outgassing may have increased. Freshly exposed ice may be sublimating for the first time as solar heat penetrates the surface. Or, less conventionally, the comet's structure may have changed, fragments breaking off, surface layers collapsing to reveal brighter material underneath. The high-rise images could answer all of these questions. Side-on geometry reveals whether jets originate from discrete locations or are evenly distributed. High resolution shows whether the nucleus is a single cohesive body or a cluster of fragments barely held together by gravity. Surface texture, if visible at all, hints at age, composition, processing by radiation. If there are anomalies, structures that do not fit the comet paradigm, HiRISE would see them. China's images from Tianwen-1 are suggestive but blurry. HiRISE is designed for precision. The frustration in the astronomical community is not just about delays. It is about watching a golden opportunity slip away while bureaucrats debate timelines. Consider what we lose if the images remain embargoed. 3I Atlas will not return. Its trajectory is unbound, meaning it will leave our solar system permanently, accelerating as the Sun's gravity weakens with distance. Every day of delay is a day when follow-up observations become harder, when ground-based telescopes lose resolution, when the comet fades into the background noise of the cosmos. The data from Mars Reconnaissance Orbiter is finite, locked in the moment of closest approach. If NASA waits too long to release those images, the scientific conversation moves on. Astronomers write papers based on incomplete information. Models get built on shaky foundations. And when the truth finally emerges, we discover we could have known earlier, if only someone had pressed the button marked Release. What is NASA waiting for? What are they reviewing? What discussions happen behind closed doors when the subject is an interstellar visitor that refuses to behave like a normal comet? The answers exist. They are sitting on hard drives, waiting for permission to see daylight. And while we wait, 3I Atlas speeds away. Carbon dioxide should not dominate. In the solar system, we know, the solar system that formed 4.5 billion years ago from a collapsing cloud of gas and dust. Water ice is the primary volatile. Comets are dirty snowballs, mixtures of water ice and rocky material with traces of more exotic molecules. 3I Atlas inverts that expectation. James Webb Space Telescope's NIR-SPEC instrument measured the comet's chemical signature in detail, finding carbon dioxide everywhere. Water is present, but secondary. Carbon monoxide appears. Carbonyl sulfide, a molecule rarely detected in comets, shows up in trace amounts. The composition suggests either an alien formation environment or post-formation processing that transformed the comet's surface into something unrecognizable from its birth state. Imagine a star system colder than ours, farther from its sun, where the protoplanetary disk never warmed enough to vaporize carbon dioxide. In such an environment, carbon dioxide freezes solid while water remains scarce or locked deeper in planetary bodies. Comets forming in that disk would naturally carry more carbon dioxide, incorporating it into their structure as they grew from countless collisions between dust and ice particles. 3. I-Atlas could be a messenger from such a place, a sample of chemistry we cannot replicate or observe except through these rare interstellar visitors. Alternatively, consider cosmic rays. Galactic cosmic rays are high-energy particles, mostly protons, that permeate interstellar space. They originate in supernovae, active galactic nuclei, and other violent cosmic events. When they strike solid matter, they deposit energy, breaking chemical bonds, rearranging molecules, creating new compounds from old. A recent paper on Archive proposes that 3I Atlas spent millions or billions of years in interstellar space, bombarded constantly by cosmic rays. Carbon monoxide on its surface could have converted to carbon dioxide through radiation chemistry. Organic molecules could have formed, creating a radiation-processed crust that now defines the comet's observable properties. What we see is not the pristine interior, but the irradiated skin, altered by eons of exposure to the cosmos. This hypothesis has implications. If cosmic ray processing is real and significant, every interstellar object carries a similar altered surface layer. Pristine cometary material exists underneath, but the outer crust is fundamentally different, enriched in carbon dioxide and complex organics. High-rise images could support this idea indirectly. If the surface shows color variations, patches of different brightness or reflectivity, those could indicate regions where the crust has been breached, exposing less processed material beneath. Swift Space Telescope's detection of hydroxyl, the water fragment molecule, adds another puzzle piece. Hydroxyl means water is sublimating, breaking apart under ultraviolet radiation from the sun. But 3I Atlas was detected releasing hydroxyl at distances where traditional comet models predict minimal water activity. Calculations suggest that a large fraction of the comet's surface must be active, releasing water vapor continuously. Alternatively, icy grains in the coma, tiny particles of water ice suspended in the gas cloud surrounding the nucleus, could serve as an extended source. Sunlight heats the grains, they sublimate, and hydroxyl appears far from the nucleus. Near-infrared data supports the grain hypothesis, showing evidence for large icy particles that survive surprisingly far from the comet's core. Non-gravitational acceleration is the technical term for when a comet does not follow a perfect Keplerian orbit. Gravity alone, the pull of the sun and planets, determines where an object should be at any given time. 3I Atlas deviates slightly from those predictions. Its trajectory curves in ways that require additional forces. Outgassing provides those forces. When jets of gas erupt from the comet's surface, they push back, creating tiny rocket engines that nudge the comet's path. Recent modeling published on Archive shows that 3I Atlas's acceleration profile can be explained by anisotropic outgassing of carbon monoxide and carbon dioxide. Anisotropic means the outgassing is not uniform. Jets point in specific directions, favoring some parts of the surface over others. The model works, fitting the observed trajectory without invoking exotic physics. But the fit requires careful tuning. Active regions must be positioned just right. Outgassing rates must match observations. The implied structure is delicate, specific, constrained. Some observers report extremely negative polarization in optical data. Polarization measures how light's electromagnetic waves are oriented after reflecting off the comet's dust. Negative polarization is unusual, suggesting dust grains with specific shapes or compositions. Rapid brightness changes appear in ground-based images, variations on timescales of hours rather than days. Color behavior is odd, with the comet appearing redder or bluer than expected depending on wavelength. These are not definitive anomalies. They could result from measurement errors, atmospheric effects, or unusual but natural dust properties. Or they could be hints that 3I Atlas is not behaving like a standard comet, that its dust is different, that processes we do not understand are occurring in its coma. What if the anomalies are not just statistical noise? What if carbon dioxide dominance, cosmic ray processing, extended water sources, and unusual polarization all point towards something genuinely strange? Not necessarily artificial, not alien technology, but a comet so thoroughly processed by its interstellar journey that it no longer fits our models. We have studied solar system comets for centuries. We have sent spacecraft to rendezvous with them, land on them, analyze their composition up close. 3I Atlas is different. It formed somewhere else, traveled through conditions we can barely imagine, and arrived in our solar system carrying secrets about another star's planetary system. The chemistry tells us that wherever it came from, the rules were different. The question is, how different, and what that means for our understanding of planetary formation across the galaxy. High-rise images will not reveal chemistry directly, but they will show structure, and structure constrains chemistry. If jets erupt from specific craters or fractures, that tells us about subsurface volatile reservoirs. If the surface is smooth versus rough, that hints at age and processing history. If there are color variations visible even in grayscale imaging, that maps compositional heterogeneity. The answers are there, locked in data, waiting for someone to decide the world is ready. Avi Loeb is used to controversy. His suggestion that Oumuamua, the first confirmed interstellar visitor detected in 2017, might be an alien artifact made him simultaneously famous and infamous. Mainstream astronomers largely dismissed the idea, pointing to natural explanations for Oumuamua's unusual acceleration and elongated shape. Loeb held firm, arguing that scientists should at least consider non-natural hypotheses when dealing with objects from beyond our solar system. Now, with 3I Atlas refusing to behave like a normal comet, Loeb is asking uncomfortable questions again. Why is NASA withholding the high-rise images? What do those images show that requires high-level review? Is the delay really about a government shutdown, or is there something else? The artificial object hypothesis is extreme, but let us examine it honestly. 3I Atlas accelerates in ways explainable by outgassing, but the required jet configurations are specific. It has an apparent anti-tail pointing toward the sun, unusual but not impossible with projection effects. Its composition is carbon dioxide rich, strange but potentially natural. Its polarization is weird. Its brightness changes are rapid. Its structure appears complex. Individually, each anomaly has a conventional explanation. Together, they form a pattern that makes some scientists uncomfortable. If you wanted to design a probe to study a solar system from the inside, you might give it a cometary disguise. You might use outgassing for propulsion, carefully controlled jets that mimic natural comet behavior while allowing precise trajectory adjustments. You might coat it in ice and dust to blend in, hiding artificial structures beneath a natural-looking crust. You might time your arrival to coincide with perihelion, when solar heating provides cover for any unexpected activity. This is speculation, wild speculation, unsupported by the bulk of evidence. But it is speculation that respected scientists are willing to voice publicly, and that tells you something about the current state of uncertainty. When conventional models require careful tuning to match observations, when multiple independent anomalies appear in the same object, the range of possible explanations expands. Natural but exotic becomes plausible. Unnatural becomes mentionable, if not probable. NASA's silence fuels suspicion. The high-rise website's statement that images of 3I Atlas are NASA-wide news is unusual phrasing. Standard asteroid or comet observations do not receive that designation. The phrase implies significance, coordination, sensitivity. Government shutdowns have delayed scientific data releases before, but usually not with this level of secrecy. Previous Mars Reconnaissance Orbiter images of comets or asteroids appeared online within weeks. 3I Atlas is approaching months without release. The discrepancy is notable. The community is noticing. China's Tianwen-1 orbiter released its images quickly, a GIF showing 3I Atlas moving against the background stars, nucleus and coma clearly visible. The craft was approximately 29 to 30 million kilometers from the comet, similar to MRO's distance. China's images are lower resolution, less informative scientifically, but they exist in the public domain. Chinese space scientists gave presentations showing the data, discussing what they learned, contributing to the global scientific conversation. NASA's data, presumably superior in every technical respect, remains hidden. The optics are terrible. It looks like a space race for information, with China playing the transparency card while the United States hoards knowledge. Conspiracy theories thrive in information vacuums. Reddit threads dissect every pixel of available images, searching for anomalies. Some users claim to see structured features in China's low-resolution images, geometric patterns that should not exist. Others argue NASA is afraid of paradigm shift, that releasing images showing something genuinely weird would undermine public trust or scientific consensus. Still, others suggest internal politics, competing research groups fighting for first authorship, bureaucratic turf wars delaying release. The truth is probably mundane. Government shutdowns genuinely disrupt workflows. Data review processes take time. Quality control requires multiple eyes. But mundane explanations do not satisfy when the subject is an interstellar visitor that might rewrite textbooks. The philosophical implications hang unspoken. If 3I Atlas is artificial, if it is a probe from another civilization, what does that mean for humanity's place in the cosmos? We would no longer be alone, but we would also be revealed as late arrivals. Civilizations capable of interstellar engineering having passed through our solar system while we were still figuring out fire. If natural but genuinely weird, if it represents comet physics we have never encountered, then our models of planetary formation are incomplete. We have been studying solar system comets and assuming they are representative. 3I Atlas says they are not. Other star systems produce different outcomes, and we have to expand our framework to accommodate that diversity. The coming high-rise images are the linchpin. They will not definitively prove artificial origin, but they could disprove it by showing obviously natural comet morphology. They will not answer every question about composition or formation, but they will constrain models dramatically. They are the single most important data set for 3I Atlas, and they are locked behind bureaucratic doors while the comet speeds away. Every astronomer who studies comets, every planetary scientist interested in interstellar objects, every person who looks at the night sky and wonders what else is out there, waits for NASA to decide the time is right. But when is the time right to tell humanity that the universe just got stranger? Electrostatic dust lifting is not a household term, but it might explain some of 3I Atlas's oddities. Comet dust is not just inert particles blown into space by gas pressure. Dust grains carry electric charge, accumulated through interactions with the solar wind and ultraviolet radiation. Charged grains respond to electric fields, which exist around comets due to the interaction between the solar winds, plasma, and the neutral gas in the coma. In some conditions, electrostatic forces can lift dust grains off the surface without requiring gas pressure at all. Jets could form from localized regions where electric fields are strongest. Anti-tails could result from charged dust grains following trajectories that defy simple mechanical intuition. This is exotic but not supernatural, weird physics rather than alien technology. The magnitude of these electrostatic effects depends on multiple variables that interact in complex ways. The solar wind's density and velocity vary with distance from the sun and with solar activity cycles. The comet's outgassing rate determines the density of neutral gas in the coma, which in turn affects how the solar wind's magnetic field drapes around the nucleus. The dust grain size distribution matters enormously because electrostatic force scales with surface area, while gravitational force scales with volume. Small grains respond more strongly to electric fields than large ones. The grain composition affects charging efficiency because different materials have different photoelectric properties, different secondary electron emission characteristics, different contact potentials when grains collide. 3I Atlas could have a dust population skewed towards small, highly chargeable grains due to its formation environment or its processing history. This would make electrostatic effects more prominent than in typical solar system comets. Laboratory experiments have demonstrated dust levitation through electrostatic forces under controlled conditions, but scaling those experiments to actual cometary environments introduces uncertainties. The electric field strength near a comet nucleus is difficult to measure directly. Spacecraft that have visited comets carried instruments to measure magnetic fields and plasma properties, but most missions did not include dedicated dust charge detectors. The calculations require assumptions about grain charging rates, field geometries, plasma densities. Different researchers using different assumptions reach different conclusions about whether electrostatic lifting is significant. For 3I Atlas, we lack in situ measurements entirely. We infer the electric environment from remote observations of plasma interactions and dust behavior, a kind of forensic physics where we reconstruct the crime scene from the evidence left behind. Dust grain cohesion presents another alternative. Most comet dust models assume grains are small, irregular, weakly bound together. If 3I Atlas's dust is unusually sticky, perhaps due to organic coatings or electrostatic attraction, grains might clump together into larger aggregates. Large aggregates behave differently in the coma. They fall back to the surface more readily, creating local accumulations of material. They reflect light differently, changing the comet's color and brightness. They could create the unusual polarization signatures observers report. This does not require new physics, just unusual material properties that fall within the range of known chemistry, but outside typical comet experience. The organic chemistry of comets is bewilderingly complex. Spectroscopy reveals hundreds of molecular species in cometary comae, many of them organic compounds containing carbon, hydrogen, oxygen, nitrogen. Some of these molecules are simple, like methane or formaldehyde. Others are complex polycyclic aromatic hydrocarbons or long-chain molecules that challenge spectroscopic identification. These organics form coatings on dust grains, altering their optical properties and mechanical behavior. If 3I Atlas formed in a particularly carbon-rich environment, or if interstellar processing concentrated organics on grain surfaces, the cohesion could be dramatically different from what we see in solar system comets. This would affect how dust separates from the nucleus during outgassing, how it aggregates in the coma, how it scatters sunlight. The color anomalies observers report might simply reflect a higher organic content rather than exotic minerals or artificial materials. Grain aggregation dynamics in low-gravity environments are surprisingly poorly understood despite decades of study. When dust grains collide at low velocities, they can stick together through van der Waals forces, electrostatic attraction, or mechanical interlocking if they have fractal structures. But the probability of sticking depends on the impact velocity, the grain composition, the presence of volatile ices that act as cement, the ambient temperature. In 3I Atlas's coma, grains are continually colliding, sometimes sticking and growing, sometimes bouncing apart, sometimes shattering. The size distribution evolves with time and distance from the nucleus. Large, fluffy aggregates might dominate close to the nucleus, while smaller fragments dominate farther out after collisions have broken the aggregates apart. This evolution would create spatial variations in brightness and color that could be misinterpreted as active source regions or artificial structures. Consider entirely new processes, mechanisms that only become important in interstellar comets. 3I Atlas spent an unknown amount of time in the space between stars, exposed to conditions solar system comets never experience. Temperatures approach absolute zero. Cosmic ray flux is constant. Magnetic fields are weak and chaotic. Chemical equilibrium is different. Sublimation might occur through quantum tunneling at ultra-low temperatures, molecules escaping from the ice matrix without traditional thermal energy. Surface layers might reorganize through radiation-driven diffusion, creating stratification invisible in solar system comets. These are speculations, ideas that push the boundaries of known comet science, but they are grounded in physics. We just have never had a reason to explore them seriously until interstellar visitors arrived. The quantum tunneling hypothesis is particularly intriguing because it operates at molecular scales. In classical thermodynamics, sublimation requires molecules to gain enough thermal energy to overcome the binding energy holding them in the solid. But quantum mechanics allows particles to tunnel through energy barriers they could not classically overcome. At the temperatures of interstellar space, perhaps 3 or 4 Kelvin, thermal sublimation is essentially zero. But cosmic rays constantly bombard the surface, depositing energy, creating free radicals, breaking chemical bonds. Individual molecules might tunnel out of the ice matrix at rates too slow to measure in laboratory experiments, but significant over millions of years. The surface would slowly evolve, losing volatile species preferentially, becoming enriched in refractory organics and silicates. When 3I Atlas entered the inner solar system and warmed up, this processed surface layer would sublimate differently than fresh solar system comet ice. Radiation chemistry in the interstellar medium is an active research area with direct relevance to 3I Atlas. Cosmic rays, primarily high-energy protons and heavy nuclei, penetrate deep into comet nuclei, ionizing molecules and creating reactive species. These reactive species can trigger complex chemistry, building larger molecules from simple precursors, or breaking down complex molecules into fragments. The chemistry operates in the solid state at temperatures where conventional liquid phase or gas phase chemistry cannot occur. Over time, scales of millions to billions of years, this radiation processing can significantly alter the comet's composition and structure. 3I Atlas could have spent 100 million years in interstellar space, accumulating radiation damage and chemical transformation that solar system comets never experienced during their brief excursions through the Oort cloud. The magnetic field history of 3I Atlas is completely unknown, but potentially important. Comets formed in the solar nebula were exposed to the sun's magnetic field and to fields generated by plasma currents in the disk. These fields can align magnetic grains, create remnant magnetization in iron-bearing minerals, affect the distribution of charged particles during formation. If 3I Atlas formed around a different star with a different magnetic environment, its magnetic properties could differ subtly from solar system comets. Interstellar space has weak, disordered magnetic fields that could have gradually randomized any remnant magnetization. Or cosmic ray impacts could have created new magnetic anomalies through shock magnetization. A spacecraft flyby with a sensitive magnetometer might detect these differences, providing clues about 3I Atlas's birth environment and travel history. Future missions are already being designed with 3I Atlas in mind. The European Space Agency's Comet interceptor mission, scheduled for launch in the late 2020s, is specifically designed to target a long-period comet, or, if timing allows, an interstellar object. The spacecraft will wait at a gravitationally stable point in space, ready to deploy when a suitable target is identified. 3I Atlas has taught mission planners what to look for, what instruments are essential, what questions need answering. NASA has discussed similar concepts, fast response probes that could launch on short notice to intercept interstellar visitors before they leave the inner solar system. The engineering is challenging. Interstellar objects move fast, approaching from random directions with little warning, but the scientific payoff is enormous. The mission architecture for intercepting an interstellar object differs fundamentally from conventional comet missions. Traditional missions launch toward a target with a known orbit, executing trajectory corrections along the way to fine-tune the encounter. But interstellar objects appear with little warning, and their orbits are only precisely determined after weeks or months of tracking. By the time the orbit is known well enough to design an intercept trajectory, the object may already be leaving the inner solar system. This demands spacecraft pre-positioned in space, fueled and ready, capable of executing a fast intercept with minimal planning time. The Comet interceptor design addresses this by placing the spacecraft at the Earth-Sun L2 Lagrange point, where it can wait for years if necessary, monitoring the skies for suitable targets. The instrument payload must be chosen without knowing the target's specific properties, a challenge for mission designers accustomed to tailoring instruments to specific objectives. For 3I Atlas, we would want high-resolution imaging to check for geometric features, spectrometers covering ultraviolet through infrared to characterize composition, a mass spectrometer to sample the coma's molecules directly, a magnetometer to measure magnetic fields, a dust detector to characterize grain sizes and compositions, possibly even a radar to probe subsurface structure. The mass and power budgets limit how many instruments can fly. Mission planners must prioritize, deciding which measurements are essential and which are desirable but expendable. 3. Eye-atlas's anomalies inform these decisions. If we think electrostatic effects are important, we need plasma instruments. If we think organic chemistry is key, we need high-resolution spectrometers. If we suspect artificial structures, we need the best cameras available. NASA has discussed similar concepts, fast-response probes that could launch on short notice to intercept interstellar visitors before they leave the inner solar system. The engineering is challenging. Interstellar objects move fast, approaching from random directions with little warning. But the scientific payoff is enormous. Chicheng-Jiang aimed the Lowell Discovery Telescope at 3I Atlas on October 31st, 2025, and captured something unexpected. The comet glowed green. Not the faint greenish tint sometimes visible in binoculars, but a vivid, almost alien green that dominated the comet's appearance. The color is diagnostic, a chemical signature visible to anyone with sufficient telescope aperture and the knowledge to interpret what they are seeing. Green comets are not unprecedented. Comet Lovejoy in 2011 showed similar coloration. Comet Ison in 2013 did too. The green comes from diatomic carbon, two carbon atoms bonded together, a molecule that fluoresces under ultraviolet radiation from the sun. Ultraviolet photons strike complex organic molecules in the comet's coma, breaking them apart. Carbon-carbon bonds rupture, releasing C2 molecules. Those molecules absorb ultraviolet and re-emit it in the green part of the visible spectrum, creating the characteristic glow. The process is well understood. What is puzzling about 3I Atlas is the timing and intensity. Earlier observations suggested relatively low abundances of carbon chain molecules. Carbon monoxide and carbon dioxide dominated the composition, with water ice present but subdued. Where is the source of all this C2 suddenly appearing post-perihelion? One hypothesis invokes the radiation-processed crust discussed earlier. Imagine the comet's surface covered in a layer of organic material, complex molecules created by billions of years of cosmic ray bombardment. Before perihelion, that crust is cold, stable, inert. Solar heating during the close approach breaks down the crust, liberating simpler molecules including the precursors to C2. The green glow is evidence of the crust's destruction, the comet shedding its irradiated skin to reveal fresher material underneath. If true, the process would continue for weeks or months post-perihelion, gradually fading as the surface equilibrates. Observations over the coming months could test this idea by tracking how the green intensity changes with time. The tail visibility issue adds another wrinkle. Some observers report that 3I Atlas's tail seems faint or nearly invisible in their images, despite the comet's brightness. Tails form when dust grains are pushed away from the nucleus by solar radiation pressure. If we are looking nearly along the tail's axis, down the barrel so to speak, the tail compresses into a small apparent size and can vanish into the background sky brightness. 3I Atlas's geometry relative to Earth might place us in exactly that unfavorable viewing angle. Alternatively, the tail might genuinely be faint because the comet is not producing much dust, gas-rich but dust-poor. Composition measurements support a gas-dominated coma, so perhaps the tail's absence is not geometry but genuine lack of dust production. Jets dominate post-perihelion imaging. Jiang's October 31st images show at least 7 distinct jet features radiating from the central condensation. Some jets point in expected directions, away from the sun, pushed by the pressure of outgassing. Others point in strange directions. Anti-solar jets, structures extending toward the sun, appear clearly. These could be projection effects, jets actually pointing out of the plane of the sky that seem to point sunward from our perspective. Or they could be real anti-solar jets, gas escaping from the night side of the nucleus, regions not directly illuminated by the sun, but warm enough from internal heat or re-radiated thermal energy to outgas. The distinction matters because anti-solar jets imply significant internal heat transport, a more geologically active nucleus than simple insulation models predict. Brightness changes are rapid. Observers report variations on timescales of hours, the comet brightening and dimming in near real time. Comets normally change brightness slowly, over days or weeks, as their distance from the sun changes or as rotation brings different surface features into sunlight. Our scale variability suggests something more dynamic. Jets turning on and off as pressure builds and releases in subsurface cavities. Surface collapses, exposing fresh ice suddenly. Fragmentation events, where pieces break off the nucleus. All of these are possible in conventional comet physics, but all require specific conditions. 3I Atlas is not a quiet, stable object. It is active, evolving, responding to solar heating in ways that push the boundaries of normal comet behavior. China's Tianwen-1 contribution cannot be dismissed despite its lower resolution. The HIRIC camera captured a GIF, multiple frames showing 3I Atlas moving against the starfield. The motion is obvious, a reminder that this is not a static object, but something traveling at over 30 kilometers per second relative to the sun. The coma is clearly visible, a fuzzy envelope of gas and dust surrounding the brighter central condensation. China's scientists presented this data at conferences, discussed it in press releases, contributed to the global understanding of the object. Their transparency contrasts sharply with NASA's silence. Whether NASA's high-rise images are dramatically better, showing details invisible in the Chinese data, or merely incrementally better is unknown. But the perception is clear. One space agency chose to share, the other chose to withhold. These breakthroughs collectively paint a picture of an object that refuses to sit still. 3I Atlas is not the boring interstellar comet some might have hoped for, a frozen chunk of ice coasting passively through the solar system. It is active, colorful, structurally complex, compositionally unusual, and behaviorally challenging. Every new observation raises questions. Every answered question reveals deeper mysteries. The comet is the Rosetta Stone, but the inscription keeps changing before we can finish translating it. Comet science has always involved puzzles. 3I Atlas has elevated puzzles to an art form. Comparing 3I Atlas to other interstellar objects is instructive. Oumuamua, the first confirmed visitor, showed no coma, no tail, no obvious cometary activity. It accelerated anyway, leading to the suggestion it was outgassing something invisible, like hydrogen, or the more exotic suggestion of a light sail. Borisov, the second interstellar visitor, was an obvious comet with clear coma and tail, composition similar to solar system comets. 3I Atlas falls between these extremes, obviously active like Borisov, but compositionally weird. Like Oumuamua was physically weird. The pattern suggests interstellar objects are diverse, each one potentially surprising us in new ways. We cannot generalize from 3 data points, but the trajectory is clear. Expect the unexpected. When NASA finally releases the high-rise images, the first minutes after publication will be chaos. Astronomers worldwide will download the files, load them into analysis software, start measuring features, comparing them to predictions from models. Online communities will zoom in, enhance, speculate. Press releases will follow. Carefully worded statements about what the images show and do not show. And then the real work begins. The slow process of turning raw data into understanding, of fitting observations into theory, or breaking theory to accommodate observations. 3I Atlas is not just a comet. It is a catalyst, forcing the scientific community to confront questions we thought we had answered. The green glow is beautiful. The mystery beneath that beauty is what keeps astronomers awake at night. 3I Atlas is a comet story, but it is also a data transparency story, a space agency politics story, and a fundamental question about how science advances in the 21st century. The revolution is not happening on Mars or in interstellar space. It is happening in the gap between observation and publication, in the decisions about what data gets shared and when, in the power dynamics between nations competing for cosmic knowledge. NASA's decision to withhold high-rise images might seem like a minor administrative delay. It is actually a symptom of deeper tensions about who controls scientific information and who benefits from keeping it controlled. Artificial intelligence is reshaping astronomy faster than most people realize. Machine learning algorithms now schedule telescope time, optimizing observing plans to catch transient events like supernovae or asteroid occultations. AI systems analyze images in real time, identifying anomalies that human observers might miss. Deep learning networks classify objects, distinguishing stars from galaxies from artifacts with accuracy exceeding human experts. 3I Atlas was discovered partially through automated systems that flagged its unusual trajectory. Future interstellar objects will be found even faster as AI gets better at recognizing what does not belong. The bottleneck is no longer detection. It is follow-up, pointing enough instruments at the right targets fast enough to capture data before the objects move on. Exoplanet science connects to 3I Atlas in non-obvious ways. When we model exoplanetary atmospheres, we make assumptions about the composition of the material that formed those planets. Carbon dioxide abundance relative to water, the presence of complex organics, the role of radiation processing over billions of years, all factor into predictions about what exoplanet spectra should look like. 3I Atlas gives us ground truth for at least one other star system. If carbon dioxide-rich comets are common among interstellar visitors, that constrains exoplanet models. If cosmic ray processing is universal, we need to account for it when interpreting observations of distant planetary systems. The connection is not direct, but it is real. Every piece of information about interstellar objects feeds into the larger framework of understanding how planetary systems form and evolve across the galaxy. Physics at the fundamental level might be involved if cosmic ray processing is as important as recent papers suggest. Radiation chemistry operates through quantum mechanical interactions between high-energy particles and matter. Understanding how molecules rearrange under cosmic ray bombardment requires detailed calculations of energy deposition, bond breaking, and reformation. The timescales are immense, billions of years of continuous irradiation. The conditions are extreme, temperatures near absolute zero, vacuum better than anything achievable in laboratories, magnetic fields negligible. If 3I Atlas has been significantly altered by this process, it represents a natural experiment we cannot replicate on Earth. Studying it informs radiation chemistry, materials science, and our understanding of how matter ages in the cosmos. Mission strategy is evolving because of 3I Atlas. Space agencies previously assumed interstellar objects would be rare curiosities, interesting but not urgent. The detection rate has increased. Oumuamua in 2017, Borisov in 2019, 3I Atlas in 2024. Improved telescopes will find more. The question shifts from if we will encounter another interstellar visitor to when, and whether we can respond fast enough to study it properly. Fast interceptor probes are conceptually simple, but engineering nightmares. Launch windows are unpredictable. Trajectories require enormous velocity changes. Instruments must be robust enough to survive years in space, but capable of capturing data during brief flybys. 3I Atlas is teaching mission planners what to prioritize: high-resolution imaging, composition analysis, close approaches to resolve surface details. The next interstellar object might get a dedicated mission if we are prepared. The key word is if. The SETI angle, the search for extraterrestrial intelligence, cannot be ignored, even if it makes scientists uncomfortable. If 3I Atlas were artificial, even partly artificial, it would be the most important discovery in human history. The probability is low, the evidence is weak, but the implications are so vast that dismissing the possibility entirely seems unscientific. SETI researchers have traditionally focused on radio signals, electromagnetic beacons from distant civilizations. Physical artifacts, probes, or machines passing through our solar system represent an alternative search strategy. Oumuamua raised this possibility. 3I Atlas raises it again. Each time an interstellar object behaves oddly, the question resurfaces. Even if all visitors turn out to be natural, the fact that we are asking the question shows how our cosmic perspective is shifting. We are no longer alone in the sense that the galaxy is demonstrably full of stuff from other star systems. Whether any of that stuff is intentional, designed, sent with purpose, remains unknown, but it is no longer unthinkable. What if interstellar visitors are common, arriving at rates of one every few years, and we simply lacked the telescopes to find them until recently. Surveys are getting better. The Vera C. Rubin Observatory, scheduled to begin operations soon, will scan the entire visible sky every few nights, finding asteroids, comets, and anomalies at unprecedented rates. Interstellar objects will stop being rare events and become routine discoveries. That changes everything. We shift from opportunistic studies of whatever happens to pass by to systematic characterization of a population. Statistical patterns emerge. We learn what is typical versus unusual. We identify which objects merit detailed follow-up versus which can be cataloged and ignored. 3i Atlas might be weird now, but in 5 years it could be just one of dozens, each with its own quirks, collectively teaching us about the diversity of planetary systems across the galaxy. Open data is not just an idealistic principle. It is a practical necessity for science to function efficiently. NASA's delay in releasing high-rise images hampers researchers worldwide who are trying to model 3i Atlas's behavior. Chinese scientists with access to Tianwen-1 data can publish results, while American scientists using better instruments cannot. The asymmetry creates frustration and slows progress. If NASA releases the images promptly, dozens of research groups analyze them simultaneously, comparing results, catching errors, building consensus, or identifying genuine disagreements. Delay benefits no one except possibly whoever wants to publish first, hoarding data for competitive advantage. This is not how science is supposed to work in an era of global collaboration. 3i Atlas does not belong to NASA. It does not belong to any nation. It is a cosmic phenomenon, a visitor to the entire Earth, and the data should be shared accordingly. The call to wonder here is not about aliens or conspiracy theories. It is about the genuine strangeness, the universe, the fact that reality keeps surprising us, that objects from other star systems are passing through our neighborhood, carrying information we desperately want. 3i Atlas is a door. We can look through it and see glimpses of another planetary system's history, another environment's chemistry, processes that do not occur in our solar system because conditions were different there. Every interstellar object is a door to somewhere else. We should be flinging those doors open, studying what lies beyond, not arguing about who gets to control the doorknob. When high-rise photos drop, assuming they ever do, the world might change. Or the world might shrug, glance at images of a fuzzy comet, and move on. The scientific community will not move on. They will analyze those images for years, extracting every possible detail, comparing them to models, building theories, planning missions. 3i Atlas will become a cornerstone of interstellar object science, the example everyone cites when discussing composition, activity, structure. Future textbooks will include its images alongside Halley's Comet, Shoemaker-Levy 9, and Borisov. Students learning planetary science decades from now will study 3i Atlas as a pivotal moment when we started to understand that the solar system is not isolated, that we are part of a larger galactic ecosystem where material flows between stars, mixing, evolving, carrying history across light years. Stay tuned, because this story is not over. 3i Atlas is still observable, still active, still speeding away toward the outer solar system and beyond. Ground-based telescopes will track it for months. The James Webb Space Telescope might observe it again if time permits. And somewhere, locked in NASA's data archives, high-resolution images from Mars Reconnaissance Orbiter wait for their moment. When that moment comes, when the files finally upload to public servers and the world gets to see what 3i Atlas really looks like from the side, we will know whether the anti-tail is real, whether the jets are structured, whether the surface shows anything we did not expect. Until then, we wait. The comet does not wait. It moves on, indifferent to human curiosity, following a trajectory determined by gravity and momentum, carrying its secrets back to the void between stars where it spent countless eons before briefly passing through our small corner of the cosmos.